Hey everyone, thanks for looking in. Cut knurling is an often overlooked or perhaps even unknown technique in some quarters of the machining universe. Unlike pressure or form knurling, which forces the material to flow under high pressure, cut knurling, as the name suggests, actually cuts the material away, leaving a very crisp knurl behind. Here you can see the chips being generated by the cut knurling process on this thin-walled aluminum tubing. Cut knurling may be accomplished with the simple tool shown here. It's nothing more than a single knurling wheel mounted on a round shaft. Here's the tool mounted in a common boring bar holder, the kind with a V-groove on the lower shelf. Here are a couple more examples of what it can do. The knurling tool is positioned at the extreme end of the work and slowly plunged to the desired depth. Cutting takes place as the tool is traversed towards the headstock, with small chips flying in all directions. A stream of pressurized air is directed onto the knurling wheel to blow off the swarf, which could otherwise damage the workpiece. This knob is mild steel. I'll put a couple of chamfers on it, part it off, then turn it around to finish it. What you see here is actual real time. The parting blade was cut out of an old woodworking carbide tip saw blade. I'll just face it off, give it a quick polish, and then we'll have a close-up look. So here it is close up, and you can see that it's not quite perfect. My compressed air blower scheme is not 100% effective in removing the little chips that sometimes get rolled into the facets of the knurl. Still, only an obsessive-compulsive neurotic like myself would bother to examine a knurl at this level of detail. I think any normal person would say this knurl looks great. Here's a piece of aluminum. Let's see what I can do with it. Wait a minute. What is this? Have I fallen through a wormhole and landed in someone else's video? This looks like some sort of crazy screw thread. Well, I guess not. This really is a knurl, or at least half of one anyway. Let's finish the other half and see what it looks like. Silly me, I forgot the air blower. It's essential to clear the chips as knurling progresses. Otherwise, they get rolled into the knurl and deface the facets. Although it's hard to see, it does a pretty good job of keeping the knurling wheel clean. Now that's more like it, but it's not quite deep enough, so I'll take another light pass. Yeah, I know this is just a demo, but let me just clean up the end with a little chamfer. Here's what it looks like close up. What I've done here is cut a continuous V-groove and then superimposed a straight knurl on top of that, just to be cute. In practice, one might want to cut the straight knurl first, as it's easier to adjust the depth of the V-groove to match the depth of the knurl. Okay, now let's take a look at how this tool is actually made. It's pretty straightforward and should be well within the capabilities of any home shop machinist who has access to a lathe and a milling machine. Here are the parts laid out, and they consist of a hardened pin which threads into the body of the tool, a washer that sits underneath the knurl wheel itself, of which there are two shown in this photo, and the cap which retains the knurling wheel. I should mention that the knurling tool you see in this video was made specifically for a 3/4 inch diameter knurl with a 1/4 inch bore and to fit in an extra tall AXA tool holder. The diameters of your knurls and the size of your tool holders may be different, and so you'll want to tailor the dimensions of your knurling tool accordingly. I started off with a piece of 3/4 inch diameter mild steel bar. I'm turning down the shank to fit into my tool holder with minimal clearance. Yeah, that's within 2/1000ths of an inch of my target dimension, and that's plenty good enough. So now I'll turn the part around and machine the head to length. As it turns out, I left it a little too long, and you'll see me correct that later. Here you see the tool blank partway inserted into the boring bar holder, with just enough space left to insert a steel shim that will prevent the clamp screws from gouging the shank of the tool. Now, in order to actually cut, the knurling wheel must be positioned at a slight clearance angle to the workpiece, typically from 1 to 5 degrees, as shown here, greatly exaggerated for clarity. I chose to endow the knurling tool with a built-in 3-degree clearance angle. Any other angle may be achieved by rotating the tool post. In order to mill the flat upon which the knurling wheel will rest, I mounted the tool directly into the tool holder, which then was secured in the vise at a 3-degree angle. Using an ordinary protractor, I made a 3-degree gauge from the thin cardboard of a cereal box. This is plenty accurate, as the 3-degree angle is pretty arbitrary anyway. Here's the flat being milled onto the tool head. There's nothing special here. The width of the flat is not supercritical. The width of the flat looks fine here, just a little bit less than the diameter of the knurl. I need to locate the center line of the part so that I may be able to drill and tap the threaded hole for the stud upon which the knurl rotates. I'm using a standard edge finder in order to locate the edge. And once I know where the edge is, and knowing the diameter of the part, I can then move the part so that the spindle axis is on the center line. The knurling wheel should be positioned such that there's a little space between it and the small shoulder, so that swarf doesn't tend to build up in that area. The exact spacing is not critical. With the drill now positioned over the right spot, the hole for the stud can be drilled and tapped. This drill, which has the same diameter as the stud, will produce a small recess in the part. The weakest part of the stud is the area that transitions from the threaded portion to the unthreaded portion. This discontinuity will fit inside the recess and therefore have a little extra support. I'm just eyeballing the depth of this recess. Now the hole can be drilled and tapped as usual. So now it's time to make the threaded stud. The stud should be hardened, and so this is being made out of water hardening tool steel. The hardening not only reduces wear, but very significantly reduces the probability of the knurl wheel seizing on the stud. The fit of the knurling wheel on the stud should be snug, with just enough clearance to allow it to rotate freely. Threading the stud takes place as usual. It's always a good idea to make a scratch pass just to be sure the thread pitch is correct. The thread, of course, could also be cut with a die, but I actually like single point threading, and I'm always assured that the thread is always true to the axis of the part. Yep, that looks okay. By threading away from the chuck, I don't have to worry about crashing into anything. For me, machining is about more than the end result. It's about process. It's about skill. It's about craftsmanship. Cutting an accurate thread with a single point tool is a uniquely satisfying experience. The art of machining provides a virtually endless supply of processes and techniques to learn. Single point threading is one of the most fundamental. I'll be using a thread micrometer to measure the pitch diameter of the thread. The pitch diameter is basically the diameter halfway between the diameter at the root of the thread and the diameter at the crest of the thread. Now, using a thread micrometer or thread wires is rather finicky. So, what's the point, so to speak? The point is, if the thread can be measured, then there's no need to test it with a mating part. The mating part may not be available, or it may be too big, too heavy, or too awkward to bring to the lathe. As long as the mating part is known to be within the specified tolerances, the two are guaranteed to fit together. The generalization of this concept forms the basis for industrial mass production. After this last pass, the pitch diameter of the thread measures just under 225 thousandths of an inch, which is within the acceptable tolerance range for this quarter 28 thread. Metric threads follow a similar scheme. I'm going to part off the stud longer than necessary and trim it to final length later. This is the cap which will retain the knurling wheel on the stud. There's nothing particularly precision here. The diameter is such that it is slightly smaller than the minor diameter of the coarsest pitch knurl I intend to use. The cap will be retained by a flathead screw that threads into the end of the stud. This chamfer is entirely arbitrary. Now to part off the cap. The thickness of the cap is not critical either. When using a file to take the sharp edges off of a groove, as shown here, the file should be pulled through the groove rather than pushed with the handle. Pushing the file through the groove may cause it to jam and produce serious kickback. Of course, the only reason I'm filing this groove is to break the sharp edge on the back side of the cap. Okay, I can use this same piece of material at the same diameter to produce a thin washer that will sit under the knurling wheel. I'm aiming for something like a 1/2 millimeter thickness or 20 thousandths of an inch, but it's not critical. However it comes out will be fine. The washer ended up being about 18 thousandths of an inch thick, or just under 1/2 millimeter, which is fine. At this time, the stud needs to be trimmed to final length. With the stud tightly screwed into the tool head, the knurl and the underlying washer are positioned in place. By the way, I recommend putting a screwdriver slot in the threaded end of the stud. It makes tightening it securely much easier. Hopefully you can see that the stud is sticking slightly above the level of the knurling wheel. The amount that it sticks out may be measured, and that will be a guide to trimming off the stud to length. It should be remembered that there needs to be a little clearance between the cap and the knurl, so leaving the stud proud of the knurl surface by about 4 thousandths of an inch or 1/10 of a millimeter should work pretty well. It turns out the stud is not the only part that needs to be trimmed to length. The teeth of the knurl should overhang the front edge of the tool head, and they don't. So I'm going to have to put the tool back in the lathe and just trim off a little from the front face. That's what comes from being a little too casual. Here's the stud in the lathe being trimmed to length. It's being drilled and tapped for an 832 screw. I'll start the tap by carefully turning the chuck by hand, but I'm not going to power tap this because the tap is fairly small and tool steel is not the easiest steel to machine. Plus, it's a blind hole. As mentioned before, the end of the tool head needs to be shaved off a little bit, and that's easy enough to do. There's only one thing left to do, and that is to harden the part of the stud that the knurl wheel rides on. I'm heating it to cherry red with an ordinary propane torch, and then quenching it in water. This is a crude and uncontrolled way of heat treating, but it works well enough. Since the steel is very brittle in this fully hard state, I temper it in the kitchen oven at about 430 degrees Fahrenheit or 220 degrees Celsius for about a half hour. With all the parts assembled, here's what it looks like. Let's see another couple of things that this tool can do. Notice here that I'm using a knurling wheel that has the teeth cut straight across, as opposed to the previous knurling wheels I was using that had teeth cut diagonally. Contrary to what one might think, the straight cut knurling wheel will cut a traditional diamond knurl. This is done by cutting two separate, opposite-handed spiral knurls. Here you see the first spiral being cut. When that's completed, the knurling tool will be rotated downward, the lathe spindle set into reverse, and the second spiral will be cut. Yep, this half looks pretty good. The knurling tool has been rotated downward, the center height readjusted, the lathe spindle put in reverse, and the second spiral is cut. Looks great. I'll just tidy up the edge with a quick chamfer. Here's a close-up view. Cut knurling works wonderfully on plastics. Here you see a piece of Delrin receiving a pretty coarse knurl. For more detailed instructions on cut knurling, see my video entitled Cut Knurling for the Home Shop Machinist. Although the knurl may be cut with just one pass, sometimes multiple passes are a better option. It all depends upon your particular setup, how deep the knurl needs to go, and the material to be knurled. Although this knurl looks pretty good, I think one more light pass will really make it shine. Yeah, that's really nice. Here's a closer look. Well, that's about it. Thanks for watching.